So this is our second video on polynomial functions of higher degree. In this one we're going to first start off again reminding ourselves what zeros are. Remember, zeros are just the x-intercepts. And then we're going to talk about the properties of those zeros and how we can use those to help us sketch what the graph would be. Okay, so let's see here. Zeros of a polynomial function. Well, again, these are just the x values when f at x equals 0. So there is a lot of ways that we can say this. Some equivalent ways of saying this is that x equals a is a 0 of f at x x minus a is a factor of the polynomial f at x and also then that a comma 0 is an x-intercept. For f at x. So they all mean the same thing. Now, before we actually do any examples with finding them, because we've done that before, we're really going to use examples of sketching along with finding here. So what do we have here? Well, repeated zeros. Suppose f at x has a factor of x minus a to the k, where k is greater than 1, and it's an integer. This is what's called a repeated zero. And has multiplicity k. Now what's the big deal here? Well, there's two things. If k is odd, the graph crosses the x-axis at x equals a. If k is even, the graph touches the x-axis. It does not cross. Sometimes I like to think of it as that it bounces off the x-axis. So let's look at a real quick example here of sketching it, polynomial function, and then we'll look at maybe another one here. So how do we sketch these? Well, let's look at the function f at x equals 2x cubed minus 6x squared. Now we're going to apply all of the things we've learned so far about polynomials, including this lead term, like the end behavior of it. So let's see here. Let's look at the end behavior. So the end behavior follows 2x cubed. So remember, you can think about, well, what is 2x cubed? It's positive, and what does it look like? The a is positive. Looks like this. So as x goes to infinity, f at x goes to infinity, and then as x goes to negative infinity, f at x goes to negative infinity. Alright, then let's figure out some other things here. So then we also have, let's find the zeros. So 2x cubed minus 6x squared. So we want to factor this. Well, I can factor out a 2x squared from both terms, and I'd be left with x minus 3, which gets me zeros of 0, and I'm going to put m here, multiplicity 2, and then 3 with a multiplicity of 1. And the only reason I'm writing the multiplicity down is so that I can know how that affects what the graph is going to look like. Okay, so then what do we do? Well, we get a graph. And we first go ahead and plot all of my intercepts, my x-intercepts. So there is a x-intercept here at 0, and then there's an x-intercept at 3. Now, I know the end behavior is all the way over here, and then the other end behavior is all the way up here. So, and I also have multiplicity of 2, so I'm going to bounce off of this point. So what I like to do is plot in a couple more points just to be careful here. And how do you plot in a couple more points? Well, you just go ahead and look at what the values are. So let's just go ahead and put in what x equals 1 is here. So if we substituted x equals 1 here, we'd have f at 1 is equal to 2 minus 6, which is negative 4. So at 1, I'd be at negative 4. And I could figure out what I'd be at 2. For instance, if I did 2, f at 2, and actually let me plot correctly here. That's not 4, that's 3. So negative 4 is right there. F at 2 would then be 2 times 2 cubed minus 6 times 2 squared, which is 16 minus 24, which is negative 8, I believe. So let's double check my arithmetic. 2 to the third is 8, times 2 is 16. 2 squared is 4, times 6 is 24. 16 minus 24 is negative 8. And so if I wanted to plot that point would be even further down here. So I'm just pausing a second. Okay, so yeah, if we want to plot this point, it would be 2, negative 8, so 4, 5, 6, 7, 8. So that would be this point right here. And then let's go ahead and do f at negative 1. This would be 2 times negative 1 cubed minus 6 times negative 1 squared, which would be negative 2 minus 6, which is also negative 8. And so this would be down here. And then we know that the end behavior, again, we're going, and I'm kind of draw it off to the side here. This isn't really part of the graph. I'm just drawing what my end behavior does. And so we can now start playing kind of connect the dots here. So I know I'm going to go down through this. Now, because this is multiplicity 2, I bounce, I touch, but I don't actually go through. And then I go down. And then I'm going to turn back up at some point because I have to, because I've got to go through this. So I'm going to say I don't know exactly where I'm turning, I'm just roughly guessing it. And then I've got to go back through this point, and I go through the point because the multiplicity is 1 there. And so this would be a rough sketch of the graph. Okay, let's look at one more here, where we do a rough sketch of the graph. Let's look at f of x equals x to the 4th minus x cubed minus 30x squared. Alright, so let's look at the end behavior. Again, this would be following x to the 4th, which is going to look parabola-esque like. Now, I'm not even going to bother writing as x goes to infinity, f of x. I'm just going to use this right here to kind of give my idea. Now I'm going to find the x-intercepts. So 0 is equal to x squared. Well, before I start factoring, I'll just write the problem down again. X to the 4th x to the 4th minus x cubed minus 30x squared. And so we'll go ahead and factor this. So we'd factor out an x squared from everything. And I'd be left with x squared minus x minus 30. So this is x squared times x minus 6 times x plus 5. Come on. Things not responding as well right now. And so this would give me, of course, zeros of x equals 0, 6, and negative 5. And then I'll write underneath them their multiplicities. So this would be multiplicity 2, multiplicity 1, multiplicity 1. Okay, now let's go ahead and sketch our graph here. And this time, I'm actually going to just give a rough sketch here without actually finding all of the other points here. So just a second here. There we go. My graph didn't want to get moved where I wanted it. Alright. That's still not perfect. Sorry about that. So let's lasso this bad boy. Move it. How about right there? Okay. So we're going to plot the x-intercepts. So 0, negative 5, and then 6. Now, I'm going to again draw my end behavior here. And my end behaviors are going up to that. And now I'm going to go ahead and start sketching. So the end behavior, so I know that I've got to come up like this. Now these are smooth, continuous curves with rounded things. So now I know I have to get back to this 0 here. And I know I go through -5 because it's got multiplicity 1. So I'm going to have to come down. I don't know how far I'm going to come down. And then I'm going to come back up here. Now this might not be in the right position. It might not be down far enough. But for now, we're just sketching these. But now I'm back up at x equals 0. That's got multiplicity 2, so I don't go through that point. I come out and bounce off of it, come back down, and I've got to come down for a little bit, but then I have to go through here. So to go through there, I've got to some point turn back up and have this be the sketch. Now this might not be exactly what the sketch is. If you were to graph this completely, it could maybe be something that looks, I'm going to draw a dotted green line here. Could look something like that. But for now, we're just trying to get a rough idea of what these graphs look like. Okay? So the last thing I want to talk about in this section, there are some problems you'll be asked to do on the homework where you have to find polynomial equations given zeros. I'll let you look through those. But this last thing here is actually, as I said, kind of a fairly important application for polynomials, and this is dealing with intermediate value theorem. Now, intermediate value theorem is actually something that can be used beyond just polynomials, but we can use it here with polynomials. So, let A and B be real numbers such that A is less than B. If f is a polynomial, such that f at A does not equal f at B, then in the interval A to B, f takes on every value between f at A and f at B. Okay, so big deal. Why does that matter? Anyway, say this is kind of confusing. Anyway, what's the point of this? Well, I'll kind of give you the application of this right away here, or one application of this. One thing that you can use this intermediate value theorem for, you can use this used to find zeros. What do I mean by find zeros? Well, if you have a graphing calculator, if you have any other calculators or advanced calculators or graphing programs, you know, you can always find them and they can find an x-intercept on there. Well, they have to do it somehow. Somehow they have to find the x-intercepts. Well, one way they can do it is using the intermediate value theorem. That's not the only way. In fact, it's not the way your calculators do it, but it is a valid way of doing it. And how does that work? Well, let's look at f at x equals x cubed plus x squared plus 1. And then look at the interval -2 to -1. Well, I'm going to skip through some of the computations here. I'm going to compute f at -2, and that is actually equal to -3. And then f at -1 is equal to 1. But that means f takes on every value between -3 and 1 between the interval -2 and 1. So what does that mean? There is a 0 between -2 and -1. Well, you might say that doesn't help me find it too much, and you're right, it doesn't, but real quickly here, let's then look at f at -1.5. Well, f at -1.5 is the following. It is -0.125. Well, that means there's a 0 between -1.5 and -1, because this is -1.25 and f at -1 is 1, so I'm going to take on every value between these 2 points, including 0. And then you can keep playing this game where we do half the interval and seeing whether you're positive and negative, and eventually you'll wind out finding the 0. So that's just one application of it. Alright, so this marks the end of polynomial functions as far as of higher degree. We still have a few other things we're going to talk about with polynomial functions.